so we left off, still kind of on this shaky terms of, is p-value big or small, and what does that mean, right? We'll, we will see this p-value a lot more, and it's good to just kind of put down a formal definition of p-value. So the p-value, first off, is a probability. Okay, and it's the probability of observing your data. And we included this class for something more extreme. If we were to assume that the null hypothesis were true. So if we assume the null hypothesis were true, what's the probability that we would observe a difference of 96.6 in our data? Or that we would observe this in our data? That's what we're asking. That's what the p-value is. And the conclusions are, if our p-value is small, we reject the null hypothesis. Okay, that's the short form conclusion. If our p-value is small, we reject the null hypothesis. In other words, the probability of observing our data is highly unlikely. It's highly unlikely that we are ready to conclude that our data did not happen by random chance alone. Sound good?
What do you mean by something more extreme?
Something more extreme. So just like with our casino example, casino coin flip, they accused me of cheating when I won 70 games out of 100. Okay? If they accused me of cheating if I won 70 games out of 100, then they surely would have accused me if I won 71 games. Or they would have accused me if I won 72 or 73 or anything more than 70. Okay? So that same accusation or that same kind of conclusion would apply whether I had 70 games or anything more extreme. Because the probability of getting exactly 70 wins out of 100 is going to be very small. So to just kind of give you the benefit of the doubt, we got to include everything else. All right, and on the other hand, if our p-value is large, not reject. The null hypothesis. And that means the probability of observing our data under the assumption of the null hypothesis is non-negligible. Okay. We are not able to dismiss the possibility as a result those results of random chance. Okay, so if you think of the casino coin flip example, I think they line up pretty well with this, right? If in one case I observed I played 10 games and I won 7 out of 10 games. Coin landed how I called it 7 out of 10 times. Okay? Does it mean I wasn't cheating? No. But the probability of that happening from random chance alone is not small. It was not negligible. So we're not able to dismiss the possibility that I won 7 out of 10 games from random chance alone. On the other hand, what's the probability that I would win 70 out of 100 games? That probability is very small. That was like 2 in 10,000, or less than 2 in 10,000. So the probability of that happening by random chance alone was highly unlikely. That as a casino, they were ready to conclude that it didn't happen by random chance, meaning I was cheating. Okay. Again, in both of those cases, it could be wrong, right? It is possible that I was so incredibly lucky, okay? Even though it's incredibly unlikely that for that to be, it is still a possibility. And in that case, I would have made a mistake. And over here, even though they can't dismiss the possibility that it was happening by random chance alone, it is possible that I was doing something to cheat also. Okay. Those mistakes are called errors in our hypothesis testing. Okay. So we have two types of errors. Okay. Well, all of this is okay. All right. Yes.
I'm still confused with under the small p-value. So the probability of observing our data is highly unlikely, and you said it's highly unlikely, but it's still possible.
Yeah. Because unless the probability is 0, anything is possible, right? It's possible for the sun to explode. It's possible that it has already exploded, and because information travels at the speed of light, we haven't learned about it, and that in the next 9 minutes we will, I don't know, die. It's possible. Highly unlikely, but it's possible, right? So, so yeah. A small p-value just says the thing that our data observed is highly unlikely, okay? But it is still possible. Okay. Everything is possible unless you have a 0. Okay. Yeah.
What exactly did you mean by non-negligible?
Oh wait, I'm not sure if I understand you. It means that it's possible that we can't dismiss it. Okay. The possibility that it happened from random chance alone, maybe it's like 10%, okay? 10% chance that happened by random chance alone. Then I'm not ready to just say, it didn't happen by random chance, okay? There's 10% chance. It's not like, I don't know. Is that okay, or?
I think so.
You think so? It's if I say, okay, let's say I say, I can predict the future, right? And I say, okay, I'm gonna predict the future, and I've got a coin, and I predict that it's gonna land heads. It lands heads, all right? Would you go, ooh, that's amazing? Or would you would be like, do it again, all right? I might be right. I said it's gonna land heads, and maybe it landed heads, okay? Does that mean that I can truly predict the future? No. I had a 50-50 chance, all right? Half the time I do that trick, I would be right. Okay, so the possibility that we observe our data being my coin landed heads is not negligible. Okay, it happens half the time anyway. So because of that, we can't dismiss the possibility that I was just lucky, and so we're not ready to reject the null hypothesis. Okay. Null hypothesis being I have no idea what the future looks like. Okay.
What would be the null hypothesis in the Vegas coin?
Null hypothesis would be I am not cheating, and the alternative is that I am cheating. Okay. Okay, let's we'll try an example, and let me teach you how to use the t-table. I haven't taught you how to use the t-table already, right? Just looking up critical values with the, or did I already teach you, like, I don't think I taught you the use of the t-table itself. Just looking up critical values. Okay. Alright, so the t-table, I think it just says upper tail probability across the top, right?
Yeah. Yes.
Okay, so the upper tail probability, it says the thing says critical values of the t distribution, and the upper tail probability is always like you draw a line and you're going the area to the right. Okay. So we have different t distributions based on the degrees of freedom. And so if we have, let's just say our t distribution has 5 degrees of freedom. Okay, let's say we go to 5 degrees of freedom. I have 0.920, and then I can't read. 1.476. Can somebody just call out the numbers?
2.015.
2.015.
2.191.
2.191.
2.422.
422. Okay, that's good. And then across the top I've got 0.20, 0.10, 0.05, 0.04, and 0.03. Yeah? Okay, this is what these numbers mean. This says, so imagine this thing that looks like the normal distribution, but technically it's a little bit fatter. I'm centered, the center is at 0, right? This says if I draw a vertical line right here at 0.920, and I shade everything to the right, the amount that I would have shaded is 20%. Okay. That's everything to the right here. If I go further, okay, to 1.476, then the amount to the right of 1.476 would be 10%. Okay? So the 20% is everything to the right of 0.920. Everything to the right of 1.476 is 10%. And then, so we can see that as I go further out, 2.015, everything to the right of 2.015 is 5%. And further out, 2.191 gives me only 4%. So the further and further I get from 0, the less and less I have in my upper tail. Okay. So the farther I am from 0, okay, the less I have in the tail. Okay, so I think it throws some students off a little bit in that these numbers get bigger this way, but the top row the numbers get smaller. Okay, and it's just because, just imagine the curve being centered at 0, or the curve is centered at 0, and we're drawing cutoff lines further and further away from 0, and we're asking how much is going to be left, how much is going to be shaded in the tail if we shade everything to the right. So the farther you get away, the farther out we go this way, the amount that's shaded in gets smaller and smaller and smaller. Is that okay? Alright, so just a quick check. If we had a T distribution with 10 degrees of freedom, how much is shaded beyond the line 2.359? 2%. So at 10 degrees of freedom, what did I say? 2.359. So if I draw a line at 2.359, we have 0.02 beyond the line. Okay with everyone? Alright, let's try another one. Let's say I have 5 degrees of freedom, and I'm drawing a line at 1.7. How much would I have beyond 1.7? 5 degrees of freedom. Hmm?
5%?
Yeah, this one, we can't give an exact answer, okay? So if I were to draw a line at 1.7, okay, at 5 degrees of freedom, well, I do know I have less than what?
2.015. Less than 10.
I know I have, okay, so the critical values in the table that exist, I have a critical value at 1.476 and one at 2.015, right? For 5 degrees of freedom. And it says if I drew the line at 1.476, the amount I would have to the right is 10%. If I drew my line at 2.015, the amount to the right I would have is 5%. But I'm not drawing a line in either of those places, I'm drawing a line in between at 1.7. So how much do I have to the right? I can't get an exact answer. All I know is that I've got more than 5%, but less than 10%. Is that okay? So my tail area, whatever it is, it's more than 5%, but less than 10%. Are there questions on that? Just want to make sure we can get this. Okay, so let's just check our understanding. Tell me if I have 6 degrees of freedom and I draw a line at 2.4. How much is in my tail?
More than 2.5%, right?
Yeah, so my tail, whatever it is, it's more than 0.025, but less than 0.03. Okay? So I mean that's a pretty narrow range. We still don't have an exact value, but we've narrowed it down into a good range. Okay. What about 20 degrees of freedom, and I'm drawing a line at 5.3.
.0005.
Yeah, so we don't know, but we do know that it's going to be less than 0.0005. Okay? And then on the other side, let's say I have 20 degrees of freedom, and I draw a line at 0.3. More than 20%, right? So again, my tail is more than 20%. Are we comfortable with this? I know some of you are.
Can you do the 5.3 again?
Yeah, so if you look at the table, the furthest the line furthest away from 0 that we have in line 20 is 3.85 or 3.8 something, okay? We need 3.85, okay? So what I'm saying here is that I'm going even beyond 3.85, okay? So I actually have no idea how much is in my tail, but I do know for sure that whatever it is less than 0.0005. So that's why we have that, okay? And then it works just the other way for lines that are close to 0. Okay. So most of the time, as we're using this table, you won't have an exact area for your tail. It's going to be capped off between two ranges. You're going to say it's between more than this, but smaller than this, or it's less than this, or it's more than that. Okay. Most of the time, that's what you're going to get, unless by happenstance you happen to get one of these exact numbers. Okay. Then you can say, then I know for sure the amount in my tail is exactly this. Okay. Otherwise, it's going to be between. It's going to be a range.
Even if it's off by like 1 decimal.
Yeah, even if it's off by a little bit, okay, you can say it's going to be really close to the one that it's really close to, okay, but yeah.
Can you just say like just over this, or just under?
Sure, you could say that. You can say that on the quiz and stuff. On the multiple choice thing, I'll just have ranges, but yeah, on a quiz, it doesn't matter, okay? And then when you do things on a computer, it's going to spit out an exact value. It's just when you're using a table, okay? But that's how we use the table. All right, so with that, let's try a problem out. So like through elementary school, the average height of boys and girls are pretty close together. But when does it just start to?
4th grade, 5th grade.
I was gonna say like 8th grade or something. Middle school somewhere. Okay, so let's say we're curious. Let's say in 8th grade, is there a difference between the average height of boys and girls? I have no idea. I really don't. Okay. So we go to 8th grade. Difference in average height of boys and girls. Okay, so let's say we go out and this is our data. we look at boys, girls, okay. 15 boys, whatever, 20 girls. What's the average height? How tall are they in 8th grade? 5, 6, 5'1". Okay. And girls, 5. Oh, that's too tall. Whatever. Okay, let's just say this is this. Alright. And the standard deviation, let's say, in 8th grade there's a huge standard deviation. So let's say 4.2 and 4.1. I made all of these numbers up, so if this is not like real life, don't hold it against me. Alright, does our data, or do our data, provide evidence that there is a difference between the mean height of boys and girls in 8th grade? I'll give you this. Standard error is in your test statistic. Okay. Let me just state our null hypothesis is that boys and girls have, in 8th grade, boys and girls have the same mean height, right? Okay, so our null hypothesis is mu1 equals mu2. And our alternative, so actually before I wrote down any data, would you have guessed one gender to be taller or shorter than the other gender? Or would you have said the girls are taller or the boys are taller, or we really don't know?
Boys.
Okay, so we could do, we can say, if we call boys group 1 and girls group 2, we can create a one-sided hypothesis, which says boys mu1 is greater than mu2. Okay, why don't I give you a minute to figure out your test statistic, and then we'll discuss where to go from there. Or see if you can find the test statistic and the p-value based on this, or tail area at least. Test statistic, and when you look it up in the table, use degrees of freedom equal to n1 plus n2 minus 2. we have a test statistic? Who do we have?
0.704.
Okay, I got close enough. 0.69. But so the test statistic, we just do 61 minus 60. That's our observed difference in means. We observed a 1-inch difference. So that minus 0. So 1 minus 0. And then our standard error, when I did it, I got 1.4493 or something like that. So I get a difference of 0.69. Okay. Alright, and then when I look that up, how much do I have in my tail from my upper tail probability? Well, how many degrees of freedom would I have? Oh, I didn't tell you how to do this. Oh, okay. So here we do n1 plus n2 gives me 33 degrees of freedom. Oh no, I did tell you this, I think. If you, anytime you can't find your exact degrees of freedom, you always round down, right? So we're going to use 30 degrees of freedom. Even if we had 39 degrees of freedom, just to play safe, we're going to round down to 30 degrees of freedom. And at 30 degrees of freedom, this says the amount in my tail would be greater than 20%. Is that okay? Alright. And this becomes my p-value, okay? My p-value is now greater than 20%. When I have a greater than or less than in my alternative hypothesis, okay, I will use my tail area as my p-value rather than double it, okay? But I also must check something called directionality, okay? So if HA has greater than or less than, do not double tail area for the p-value. Okay, just use the tail area as your p-value. Okay, but check directionality, and I'll get to that in a minute. Okay, but before we get to this directionality, so here I come to the end and I say p-value is greater than 20%. Is that okay with everyone? What should my conclusion be regarding the null hypothesis? Do I have or do I not have evidence to reject this null hypothesis? So my null hypothesis says that boys and girls in 8th grade have the same mean height. Does this provide evidence against that, or does it not provide evidence against that? What's that?
It provides evidence against it.
Oh, I was just going to say it does not. It does not, okay? So even though I have a difference of 1 inch, okay, it turns out that I would get a difference of 1 inch or more over 20% of the time. Okay, and because that's a big value, I'm not ready to conclude that there's a difference in the respective populations. Okay, so here my p-value is big, so I do not reject the null, which means I do not have evidence that this is wrong. Okay, so p-value is large, so we do not reject the null. We do not have evidence that mu1 doesn't equal mu2. Okay, or we do not have evidence against the null hypothesis. Or we do not have evidence that mu1, I should say, is greater than mu2.
What's the cutoff between a small versus big one?
Yeah, I will talk about that right after I cover check directionality. These are all good questions, and they all like what we're doing should naturally bring up these questions. But I just have to cover these things one at a time. Okay, is this okay? Yes. Okay.
Could you just repeat one more time why we don't double the p-value again?
This is it's the rule. It's called a one-sided hypothesis test. A one-sided hypothesis test has an alternative where this is greater or that's less than. Okay, because prior to this, prior to gathering our data, even though we didn't do it this way, we said, well, we would expect the boys to be taller than the girls. We would expect the 8th grade boys to be taller than the 8th grade girls. Okay, and our data. Well, the sample mean, 61, is indeed higher than 60. The question is that difference statistically significant or not? And according to our math, it is not statistically significant. The boys are, our sample does show that the boys are taller than girls, but that difference is not statistically significant, is what our p-value shows. Okay, if there's any questions, please don't hesitate. Alright, so let me talk about this idea of checking directionality. If, let's say, prior to gathering the data, let's say somebody says, you know what, in 8th grade, girls generally have their growth spurt fast, I don't know, before boys do. I don't know. I think that's true, right? And they generally, everybody goes through puberty at different ages, but generally the growth spurt for the girls, I think, happens before it does for the boys. Okay, so somebody might say, well, 8th grade is that time when girls should actually be taller than the boys on average. Okay, and so somebody might say, I think I want to know, do we have evidence that 8th grade girls are taller than 8th grade boys? Okay, and in that case, they would set up their alternative hypothesis. Get rid of everything else. They would set up their alternative hypothesis as that. They would expect mu2 to be greater than mu1. This one says we want, do we have evidence that 8th grade girls are taller, that 8th grade girls average is taller, 8th grade girls mu is greater than boys 8th grade boys mu, okay? Okay. So they do that. That's the question. Do we have evidence that the girls are taller than the boys? We go and we gather our data. And this is what happens. Okay. Well, when we do our check for directionality, that just means we, does our data even support this notion? In our data, it turned out that the boys on average were taller than the girls. Okay, our sample of 15 boys had a higher mean than the sample of 20 girls. So would our data provide any evidence that girls are taller than boys? No. Okay, so there's no way for our data to provide evidence for this alternative. So in that case, our data will not provide evidence that mu1 is less than mu2. Okay? Our data shows y1 bar is greater than y2 bar. Okay? So that's not going to support the idea that mu1 is less than mu2. So in that case, our p-value, okay, we go through, you know, all the math is still the same. Okay, 61 minus 60, all of this stuff is still the same. Alright, and then when we looked it up in the tail, in the t-table, we said our tail is greater than 20%. Okay? When your data goes contrary to the directionality, the amount in the tail flips around. You do a 1 minus. So in this case, you have to pretend it's not the tail. So here we know that our tail is more than 20%. So we know that our tail is more than 20%. On the other hand, the flip side would be the hill. So I don't know what you would call it. Okay, but the hill would then be, what, less than 80%. Okay, so our p-value would be less than 80%, but also we know it's more than 50%. It's not so important, but we just have our p-value is more than 50%, but less than 80%. Can we see that? So in this case, had we set up our alternative and our data goes contrary to our alternative, then we have this reverse situation. Okay. You actually don't even have to go through it. Okay. Anytime your data goes contrary to your alternative, you know your p-value is going to be over 50%. Okay, that's another shortcut. Okay, if your data goes contrary to the alternative, then your p-value, whatever it is, for sure is going to be over 50%. Okay. P-value for sure be 50%, and you will not have any evidence to support the alternative.
In our previous example, our p-value is greater than 20%, right? And we said we do not have evidence. Actually, we do not have evidence to reject null hypothesis, which also means it does not support the alternative.
Yes.
But that's not greater than 50%.
Huh?
But that's not greater than 50%.
It doesn't have to be greater than. It just, the p-value has to be large for us to say we do not reject the null.
So what do you mean by the alternative has to be greater than 50%?
No, my p-value is, in this case, with my data going contrary to what the alternative says, right? My alternative says mu1 is going to be less than mu2. But my data shows that y1 bar is greater than y2 bar, okay? So in this scenario, which is different from the previous one, in this scenario, I will have no evidence to support the alternative. Okay, and I can just right away say my p-value is going to be over 50%, and I am not going to reject the null.
Okay.
Okay. So I don't reject my null with this alternative, and then with the other alternative I didn't reject the null. Basically, this data is just inconclusive, right? My sample's not big enough, or the observed difference I have is just not big enough. We're not going to reject the null of this data in either situation. Is that okay? I know it's a lot. It's a lot. Let's and then if in the last situation, if I put a not equal sign there, what would my p-value become? So my tail is over 20%. Here, because my alternative has a not equal sign, I have to double my tail area to get my p-value. Okay? So because HA has not equal sign, this is a two-sided test, or two-tailed test. Two-tailed or two-sided test. So I double the tail to get my p-value. So my p-value is equal to 2 times the tail. So now so that tells me my p-value is greater than 40%.
So when you're trying to figure out the p-value, you have to first go through all of those steps, and then you have to look and see what the alternative is.
Yes.
So you start with assuming the null,
Yeah.
then you have to look at what the alternative is in order to figure out what the p-value is.
Right. Okay. So everything is done assuming if the null hypothesis is true, what's the probability of observing my data? But then the ultimate probability depends on your alternative, whether you are looking at the right or the left or the double. Okay. So here my p-value is greater than 40%. Okay, and our conclusion is still the p-value is large, so we do not reject the null hypothesis. Alright, so how do we decide what is a large p-value and what's a small p-value? Alright, this is where we choose something called alpha. So at the beginning of the test, we're supposed to select an alpha. Select an alpha. Alright? Alpha is the point, is a line that you draw in the sand. It's an arbitrary line that you say, if my p-value is bigger than this number, I'm going to say, do not reject the null. If my p-value is smaller than alpha, I'm going to reject the null. If the p-value is greater than alpha, do not reject the null hypothesis. And if the p-value is less than alpha, reject the null hypothesis. Your selection of alpha is up to you, and it should depend on the circumstances that you are in. So depending on your circumstances, you may want a large alpha or a small alpha. You may say that A 2.7% probability is large. And that if you selected a small alpha. Or if you selected a large alpha, you would say a 2.7% probability is small. Okay, it depends on your choice of alpha. The most common choice for alpha is 5%. Okay, alpha equal to 5% is the most common choice. There should be some thought going into your choice of alpha. And this is one of the criticisms of the classical approach to statistics, is that 5% has become so common that people will just choose 5% without thinking about it, and most people will just go along with it, okay? But really, 5% may not be the best choice all the time, okay? How to choose your alpha is more of a nuanced thing of opinion, and it comes into play. I don't know if I have time to talk about it today when we discuss our errors, okay? But your choice of alpha, you can choose alpha 10%, you can choose alpha 2%, you can choose alpha 1%. You can choose any value of alpha, really. I would steer away from alpha larger than 10%, okay? Where alpha 5% is probably the most common choice, okay? But any alpha smaller than 10%, bigger than 0% is probably okay. And that's how we decide if alpha is big or not. Okay. Is that all right? So let's, so with this problem here, we found our test statistic to be 0.69 and our p-value was 40% or whatever. We concluded that we do not have evidence that boys and girls have a different mean height. Okay. We've actually already learned how to do this with confidence intervals. Okay, so t-tests are kind of a flip side of the coin to a confidence interval. In a confidence interval, we would have done y bar minus y bar 2, y bar 1 minus y bar 2, plus or minus a t star times the standard error. Okay, we're actually using the same standard error. Okay, and the t stars come from this same table. Okay, and it turns out that a 95% confidence interval is equivalent to performing a two-sided t-test with alpha equal to 0.05. Okay, so making a 95% confidence interval is equivalent to a two-sided t-test with alpha equal to 0.05. Okay. So if you make a 95% confidence interval and you find evidence for a difference between means, something exciting is happening after.
Pretty intense.
Yeah. It's like the epic graduation.
No, my graduation was not like this at all.
What?
It's a centennial campaign fund or something.
Centennial
It's a fundraiser.
Fundraiser? Yeah. Wow. What are they?
Right in front of Pal. They have a huge DJ.
I feel like we're missing out. Maybe you can sneak in after class. Okay. So let's say we made a confidence interval, okay? So if our confidence interval mu2. So let me just say that mu1 doesn't equal mu2. Then a t-test with alpha equal to 0.05 would come to the same conclusion. Well, this is an epic statement after all, so we're making a grand speech. So if our confidence interval provides evidence that mu1 and mu2 are different, then our t-test with, what if I need to say 95% confidence interval will come to the same conclusion. So what does our confidence interval have to look like if mu1 doesn't equal mu2? Is 0 in that interval or not?
Yeah.
No. Okay? If there's evidence that they're different, then that means the entire interval is either entirely positive or entirely negative. Okay? 0 is not in between. Okay? Meaning, I'll get to that in a minute. So the entire interval, the interval does not contain 0. Here, so if the confidence interval doesn't contain 0, then for us to come to the same conclusion with alpha, what our p-value is what? Our p-value would be bigger or smaller than alpha? Smaller than alpha, right? So our p-value is smaller than alpha, or p-value is less than 0.05. And then vice versa. If the interval did contain 0, then we know our p-value is bigger than 0.05. Is that okay? Alright, here's a tricky question. What if instead of a 95% confidence interval, okay, I did a 90% confidence interval? So I'm using the exact same data. My data here provided at 95% confidence, my data provided evidence that mu1 doesn't equal mu2. If I use the same data and I made a 90% confidence interval, would it provide evidence that mu1 doesn't equal mu2?
Maybe.
Alright. Okay, so if let's say so for the interval not to contain 0, it has to be either entirely positive or entirely negative, right? Let's say this is my 95% confidence interval. If I change it to 90%, does my confidence interval get wider or does it get smaller? It gets smaller, okay? So it didn't contain 0 when my interval was like this. If I make my interval like this, will it contain 0? Is there any chance for it to contain 0? It didn't contain it here, I've done this. So it doesn't contain 0 here. So if I change it from 95% to 90%, the interval will still not contain 0, okay? So if this is the case, if I go to 90% confidence interval will not contain 0 either. Alright, what about my p-value? If I did my t-test at 0.05 and my p-value is less than that, so I rejected it, is my p-value also going to be less than 0.1? Right? 90% confidence interval is equivalent to using alpha. Alpha is now 0.10, is my p-value bigger or smaller than 0.10? My p-value, up here we saw that my p-value is less than 0.05, so we also know my p-value is for sure going to be less than 0.10. Is that okay? Am I just exhausting you guys a little bit? Oh gosh, okay. We're running out of time. I wanted to cover one section in chapter 8, but I think because I skipped this, I didn't do the lecture last week. We're going to run out of time today. That's okay. Okay, we have a quiz next week. I'm going to have to throw out one of the problems because we haven't covered that stuff. Let me just cover this relationship between confidence intervals and t-tests. I'll just do a couple more example problems because you will see some quiz questions like these, and I just want to make sure I've given you a fair chance at them. Alright, so let's say we perform a t-test with alpha equal to 0.05. Okay? The null hypothesis is that mu1 equals mu2. The alternative is that mu1 doesn't equal mu2. This is alternative. We go through it. We conclude that there is no evidence or that we do not have evidence to reject the null hypothesis. So what does that say about our p-value? Alright, well based on this, if we did the exact same test, or if we use the same data, did the test again, with alpha equal to 0.02, what conclusion would we make? What about alpha equal to 2.10? One more. If I use the same data, to make a 99% confidence interval, would that interval contain 0? Okay, I'll give you 1 minute to work on that, just because we're going to run out of time, or we are running out of time.
These are just statements, right? There's no numbers to be calculated.
Right, everything is based on this. Yeah, there's no numbers to calculate. maybe I will give you the answers, just so you guys can go home, and maybe you can write the answers on the other side of your paper or something, and then you can kind of look at this and see if you understand this. All right. So the work over here is that this setup of the problem tells us that whatever our p-value is, it is greater than 0.05, right? We conclude that there's no evidence to reject the null. Tells us that my p-value is bigger than alpha, and my alpha was 0.05, so I do know that my p-value is greater than 0.05. Okay? So with that in mind, if I did the same test with alpha equal to 0.02, I know that my p-value is greater than 0.05, which necessitates that it's greater than 0.02. So I would come to the same conclusion. Do not reject the null hypothesis. Over here, with alpha equal to 0.10, we do not know. P-value may or may not be bigger than 0.10. Right? So p-value may or may not be greater than 0.10. So we do not know the conclusion. If we use the same data with a 99% confidence interval, where that confidence interval contains 0, okay, this is equivalent to alpha equal to 0.01, and we know our p-value is greater than 0.01 because it's bigger than 0.05. If it's bigger than 0.01, we would not reject, do not reject the null hypothesis, no evidence of a difference. No evidence that mu1 doesn't equal, or no evidence that mu1 doesn't equal mu2. So that confidence interval would contain 0. That's it. Okay, so we'll stop there. Take a peek at what we have in chapter 8, but I'll cover that next week.